Okay, so let me quickly remind you what we did last week. Essentially, I want to spend more time on trees because this is what we are really going to work on today. But I introduced last week this notion of best reply correspondence, and I emphasize, be careful, what is called a correspondence is not a function in the sense that it doesn't really take value in this set, but in the set of subset. So the correspondence take value in a set of subset. And there was a definition for this highest best reply correspondence. It takes n-1 variables and send it to a subset of AI, and it's defined in terms of argmax. This argmax is something very useful, so you can use it for many purposes. So if you have never seen this, it's probably good to check what is the meaning of this. It's where the function takes a maximal value. And if you take this for each I, and then you construct a function where on each entry you put one of them, it's denoted like this, you get a function from this set A to the set of subset. And in fact, the fixed points on this function give you the Nash equilibrium. So it's a way to find the Nash equilibrium algorithmically. You can use this to find this specific point. Then I just introduced the notion of matrix game. There are special case of bimatrix games. I introduced these bimatrix games. And if you take zero sum for two players, you get a bimatrix games. And I remind you that a bimatrix game is just a representation with matrices of what we had seen before for a two-player finite strategic game on its extension. And something important for these, I also recall that they all have a Nash equilibrium, and there are some algorithm for finding the best or the optimal strategies. Okay. And I just mentioned one thing, but it's then technical, is that among the Nash equilibrium, some have additional properties. So people have studied these additional properties. I didn't go in this direction, but yeah, if somebody is interested, you can find some information about this. Okay, so this is the end of one chapter, and then we move to the next one. And I introduced some terminology related to graphs. So I introduced what is a simple graph. A simple graph has only, whenever you have two vertices, it has only at most one edge. You don't have multiple edges, and you don't have loops in simple graphs. I introduced the notion of paths. When a path is closed, it's a cycle. And when you have a simple graph which has no cycle and which is connected, so it's in one part, it's a tree. And a rooted tree is just a tree where you decide that one specific vertex is a root. And usually you put it somewhere at a specific place, but it can be anywhere. It's just a specific vertex that you call the root. But once you have a root, you can define the distance from the root to other vertices. When you take one vertex, you can define what are ancestors or ascendant, or what are descendants. So ancestors are closer to the root, and descendants are further away from the root. And among the ancestors, you have one parent. Every vertex has only one parent, but it can have one or more children, which are further away. So children are part of the descendants. Parents are part of the ancestors. And on a tree, or a rooted tree, we also define what are the leaves. These are the leaves. They have no child or no children. They are far away from the root. And the set of leaves, of course, is all these points. And just for some notation, I call a graph X. It's made of a set of vertices and a set of edges. Then for rooted tree, the root is usually denoted by x0 or sometimes just by 0. Gamma of x if you fix a x here, gamma of x is the path from the root to x. So it's these are made of vertices. And it's unique because there is no cycle in a tree. And the set of leaves is denoted by L. So these are the endpoints. And if you look at the set of vertices minus the set of leaves, this is everything, I mean, all the other vertices except the leaves, and they are called internal vertices. So it's good to remember these words because we will use them today. Of course, if you have any question, you can interrupt me at any time. The same for those online, you can just unmute yourself and ask questions. And in this section, there is still one thing I want to introduce, is the notion of partition. It's just a very small thing. So if you take a set omega, what is a partition? It's just a subdivision. This is a partition, so I will write a sentence. So it's you subdivide omega into a couple of subsets. So a partition of omega, omega can be anything, and later it will be the set of vertices. But a partition of omega is a family. So it's a family of omega 1, omega 2, up to omega n. Or maybe I take m, because later it's not always related to the n, which is a number of players. So it's a family of subsets such that they have empty intersection. So omega j intersection with omega k is empty. Is empty if j is different from k. And of course, the union over j of omega j has to be omega. So altogether, they generate omega, but they have empty intersection. This is a quite simple notion. But I will need one more thing. And what, for the notation, we write. Just if I want to make it short, instead of this union, sometimes we write this, a union, but which is square of omega j is omega. It means precisely that they have no intersection. So it's just a notation for this union, which is a square union. So it's a disjoint union. This is disjoint union. This is a partition. Now suppose we have a partition and I want to subdivide further. So suppose in omega 2, I want to subdivide into a certain number of subsets. Omega 3, I want to subdivide it into some subset and so on. So this is a further subdivision. So if omega I is further partitioned, if we want to subdivide it further, we set omega I is a disjoint union over J of. So be careful about the notation. This small set, this one is going to be small omega 2, 1, because the first 2 is related to the fact that it is in big omega 2. Here we have omega 2, 2. We have omega 2, 3, omega 2, 4, omega 2, 5, and omega 2, 6. So the first number is referring to the first partition, and then we subdivide. Okay. So it means omega I subdivided into small omega ij. Okay, so this is the index The first one is the index of omega I, and then the second one is the index for the subdivisions. The subdivisions of omega I. We further decompose it. And just for the notation we set, it will be clear. I mean, we will work with example today. No, let me take more space. We set, I will write capital W for this set omega ij I. So what does it mean? It means I cannot really write more than this because look, it's difficult to write more precisely because the first one on this example is divided in two. So I is between 1 and 4, but then the j depend on I. For the first one, I have 6. For the second one, for the second one, the j is from 1 to 6. For this one, it would be 1 to 2. For this one, it would be 1 to 4. And for this one, there would be only 1. So I cannot really write more precisely things about the j. It would depend on for each I, the number of j would be different. But I think if you have this picture in mind, it's clear. And this W is just the union of all these things. And we say that this partition or this subpartition, because it's a second partition, subpartition, is compatible with the partition omega. What do I mean by this? What I don't want to have is to have a small omega, which is part of both sets. This is not allowed in what I'm writing. I cannot have this small omega, I don't know, 5, 4, whatever it means, which is on both, partially in this one and partially in this one. This is not allowed. That's why we say it's compatible with the first partition because it's really inside each of them. So it's not difficult to understand. It's more difficult to write. Any question? If it is a partition, yes, by definition, a partition, the union is always everything. Yes. Okay, so now we can start the new section. And the first time you look at it, it looks complicated, but then you will appreciate. So it's called extensive form gain, extensive form. Because everything is going to be on trees. So let me on this blackboard make a big tree, and I will slowly use it. So let me draw a tree. You're not obliged to do exactly the same, but it will be used. I will use it exactly in this way. Okay. This is a true, and the root is this one. And you need at least 3 colors. Oh, yes, 3 colors. So we are going to consider n players. N is always the number of players. N players game. But with an additional player 0. So you can wonder why I speak about n players, and then I'd say there will be an additional one, which I call 0. 0 is going to be either what we call the nature or the chance or randomness. Which means it's not a real player. That's why we put it slightly separately, but it plays a role. So, and just for information, there is no payoff function, and no rational behavior. I don't know if nature is rational or not. No rational behavior or 0. So we don't impose that nature is rational. It's just going to be something random. We will see. So we have n players and an additional one, which is the nature or the randomness. So this is a setting. So now, and it's a very long definition. N players, extensive form game. Is, I will go denote it by gamma. This letter, it's a capital gamma. But gamma is made of many things. There is X omega W C U. So I need to define everything. So we have 6 letters: capital X, capital omega, capital W, capital C, P, and U. So I need to say who are these guys. So with first X, you should guess because I just mentioned it. X is a tree, a rooted tree. Rooted tree. So we have the example there with root x0 and leaves. The leaves are, the set of leaves is L. So here the set of leaves are these points. These are the set of leaves. X0 is already mentioned, and all these points belong to L. So we need a tree. Then what is 2? So the second one, the omega. Omega is a partition of L minus V. So be careful, this notation, it means, I can write it, there are 2 different notations. It's L minus, no, sorry, this is not correct. It's V minus L, V minus L, V minus L. So it means I do a partition of all vertices except the leaves. So I'm going to use colors for this partition. So we have this one. The red is for omega 1. And omega 1 is a red. Then we have omega 2, this one, and this one. This is omega 2. Omega 2, so it's a partition. Then we are going to have Oh, it's a two-player, using only 2 players. So then we have this one, and this one. This is going to be omega 0 because it's going to be the nature. So we have a partition of V minus L in the set omega 0, omega 1, up to omega n. If we have n players, we have these n things. So here n is equal to 2. N is equal to 2 in this picture. So we have nature. The omega 0 is the nature. And then we have 2 players. And they do a partition. Look, I colored all points except the leaves. So I respected the second condition. No, you can really decide how you want to do the partition. There is no condition. Now, number 3. So we already explained this one and this one. Now this W, I already mentioned W is going to be a subpartition. So the number 3 is W is a subpartition of this set. Be careful of V minus L and minus omega 0. So it means I disregard the leaves and I disregard the nature. But I consider a subpartition, so it means this W is a set of omega ij. And the only thing I can say is that I is from 1 up to n. J, it depends.
The leaves was in one of the partitions.
Look at the definition. I excluded the leaves. So what does it mean? Remember, I need to do, so we have 3 points, 3 red points. We have 3 blue points. I want to do a subpartition. So I will do a very simple one. I will put together these 2 points. So I will call this set, I will call it W or omega 2,1. Then we have omega 2,2 here, because the first 2, it's related to the second player. And then we have a partition into 2 things. And I will also call this W11 or omega 1,1, omega 1,2, and we have omega 1,3 here. So you can see for the first player, the partition is very simple because each point is a partition an element of this subpartition. On the other hand, for the second player, I put 2 points together. And we will see what it means in a second. But we understand we had the blue and the red, and I can put some blue together and some red together if I want. But there are some conditions. It means satisfying. There are some small conditions which have to be satisfied. First, this W is compatible with the first partition, but it's correct on the picture. So with omega 1 up to omega n. Remember, omega 1 up to omega n is without the leaves and without the nature. The 0, the yellow one are the nature. So it is compatible because I do not mix blue and red. And the second condition, which is also respected here, for any x belonging to the leaves, What is this condition? It looks complicated, but it's not so complicated. So first, what is gamma of x if x is a leaf? It's simply a path from one point from the root to a leaf. And the condition is it can intersect here we only have one special case. It can intersect this blue part only once for each pass, and indeed, each pass from the root to the leaf intersects this at most only once, which means I couldn't do, for example, this point were blue, if this point is blue, I couldn't do this because then it would intersect this path 2 times. And it will have a meaning in a second, but I need to write it. And the third condition for this look, in my blue set, the 2 vertices have the same number of children. And this is important. Look, this point has 3 children. This point has 3 children. This one has 2, but it doesn't matter because it's not in the same. So let me state the third condition, 1, 2, 3. For any x belonging to omega ij, or all x, sorry, I should write all x have the same number of children. It doesn't mean that all vertices have the same number of children. It means in each omega ij, the number of children should be constant. So when there is only one point, it's not a condition because only one point, it has 3 children. There is no condition. But here we have 2 points in one omega ij. In omega 2, 1, we have 2 points, so it has to have the same number of children. Okay. Any questions so far? I told you it's going to be meaningful very soon. Now I'm going to, no, I will use white. As I said, these 2 points have the same number of children. I will make a difference between these edges. So I pair them. You can see, it means the first one will be related to the first one. The second one will be related to the second one. The third one will be related to the third one. And what is behind this is, in a second, we will see these 2 points will not be distinguished. You may be here or here without knowing exactly where you are. So it means what you face when you are here or what you face when you are here should be the same because you don't know where you are between these 2 points. So let me write now this condition related to this picture. A partition. So what I'm going to do, I'm going to so far I subdivided the edges, the vertices. I put a color on all vertices. Now I will consider the edges. So for edges starting from one point, there is no problem. But whenever we are exactly in this situation, as I emphasized, I have to be careful. So this is this condition. So a partition, which I have to denote C, I, J, K. So with 3 indices. So C is equal to this thing. It's a partition partition of all edges starting on the set of vertices minus the set omega 0. I can also, I don't have to speak about L because they have no children. Leaves have no children. So I just don't need to pay attention to this one and this one because they start from nature. Oh, and this one as well. I don't need to pay attention to this one because they are starting from the nature. But for all the other one, I need a partition with a condition such that let me write the sentence, such that if X belonging to this Cij has L children, should keep in mind the blue set. Everything, all the problems are coming from this blue set. So if X in this blue set has L children, in particular 3 children,Cijk contains exactly one edge. From each vertex of or in omega. Okay, so let me put some names here. So remember this set is a W21, so it means this edge is going to be C211. And the same here, this is also in C211. C211 contains one edge. Oh, sorry, it's related to the edge. It's not the ending point. So I should not make it at the end point. I should do it here. C211. And here we have C211. Then the second one, C212. And here C212. And the third one is C213. C213. The order is in there, it doesn't matter. I mean, you can just flip these things. This is not it. So read the sentence again. I need to partition all edges starting on V minus X, on V minus this, the point of nature. And so that if we take a X in one, this is a W. Is in omega of ij, has L children, Cij, K contain exactly one edge for each vertex in. And this is for K is equal from 1 up to L because they have L children. Elsewhere, we have no condition. Look, at this point, I have a C111 and a C112. This is for this edge and this edge. There is no condition. It's only for this very special set. Okay, now this was the most difficult condition by far. Now, nature, as I told you, it's going to be related to randomness. So I will give a weight or number between 0 and 1 to all edges starting from the nature. So the nature will tell me we have 60% of chance to go in this direction, 40% to go in this direction. The same here, nature is going to tell me, oh, you have, let's say 0.9 and 0.1. And here, for example, 1 and 0. So it's going, nature is going to decide the probability on edges starting at nature. So this is the condition 5. Look at the beginning of this definition. We had also a small p. So what is small p? The map p associates to any x in omega 0 a probability function on edges, probability function px So in the definition of this extensive form game, we had a P. It's simply at each point from nature. So here at each point in omega 0, I distribute a probability function on edges. That's it. Okay. And finally, the number 6, which was U, we have a utility function U, which is U1 to UN. And this is a function from the set of leaves to R. So it means at each leaves, I associate a number for each player. So we have 2 players. So let's say we would have 2 numbers. This is the payoff for the first player, for the second player, 2, 3, 1, -1. It's arbitrary now. 1, 4, 10, 0, and so on. So this is a payoff. So this is what I have introduced. And now I will explain again what it means. But if we remember, we had 6 objects. The first one is a graph. Then the set of vertices, we color them with a certain number of players plus nature. This is these colors. Then we do a subpartition of this one, like I did here. I call this omega to 1. The other one, I keep them just with 1 point, so it's simple. And then the number 4 was this complicated way of distributing edges when we are at 2 points in the same subdivision or in the same subpartition. We need to put 2 edges together, 2 edges together, and 2 edges together. And then finally, nature gives a distribution on edges starting at points of the nature. And the final object is this payoff function, which associates to each leaf a number for each player. It looks complicated, but if you think about it, it's not so complicated. The only thing is, what is the meaning of this? And we will see. So if you remember graph theory, we have more structure than on graph. Of course, on graph theory, we had not all these things. Yes, but this partition is a bit special. And now I need to give you lots of explanations. But when I did the picture, it already contains quite a lot of explanation. So first, for any x in the set of leaves, the path from the root to the leaf is called a play of the game. So going from the root to one leaf is going to be one game. And yeah, we will see more. So I recall that this gamma is a path from x0 to x. So this is called a play of the game. This is the first information. So then the partition, or let's say differently. The vertices x inside omega I is where player I has to make a choice or to take a decision, has to make a choice. So player I is only playing at the point of omega I, which is quite natural. So these points, or these, I use points, nodes, and vertices for the same thing. So one, this is a point, it's also a vertex, and it's also a node. We use the three names. So the nodes, or the vertex, I can write it like this. The vertex are called decision land. Because somebody has to take, so the vertices are called decision nodes. And if, so it means the red one are decision node for player one, the blue one are decision node for player two. Nature is taking decision on elements of omega 0. If you have any question, if it is not clear, please interrupt me. It's quite a lot of information, so don't hesitate to ask. Then peaks. Peaks is a probability. I already mentioned it. It's a probability that nature gives on each edge of x inside the set omega 0. And this is the numbers I put. Then finally, U provides the payoff for each player at each leaf. This is the easy part.
Because you have px, like it's not to what?
Of course, if it is a probability, this probability function, this number plus this number has to be equal to 1. This number plus this number has to be equal to 1. This number plus this number has to be equal to 1. It's a definition of a probability. No. You have to think dynamically. We are going to move on this. So you have 60% chance to go through this path, 40 through this path. The same here, you have 100%, 0%. You should think like this. I told you it's going to be a dynamical thing. So we are really starting at the root, going to some place. Okay, now I need to speak a bit about this omega ij. And maybe if you are doing some computer science, you will know this concept. So for each I, this omega ij, so be careful when I write it like this. It means I fix an I and I look at all omega I something. So here we have omega 2, 1 and omega 2, 2, or I could look at omega 1, 1, omega 1, 2, and omega 1, 3. So for each fixed I, this corresponds to it's called the information set, the information set of player. And this is a notion. I put a small explanation in the notes. What does it mean? It means the player I, or here the player 2, has the same information when he's at these two places. And why will it be important? It's for games when you don't, if you know everything from the start, it will be simpler. But sometimes you don't know what happened before. And it means we are going to say these 2 points are not the same inside the game, but for player I, at this moment, these 2 points are equivalent. So it means the player doesn't know if he's here or if he's here. And this is called an information set for the player I. So by its partial information, we don't have the full information. That's the interesting thing. By its partial information, the player I cannot distinguish the vertices inside omega ij. So it means the player I can, or the player 2 in this case, cannot say where he is. And this is why we need to have the same number of children. Because if we had 3 children here and only 2 here, these 2 places wouldn't be equivalent. So we need the same number of children here and here, because the person here doesn't know if he's here or here. So he needs to face exactly the 3 same options. And this is why also we put these 2 things together, because if he chooses the first edge here, it means he's also choosing the first edge here. Ask not too many questions, please. Wait for a second, think. If you don't know where you are, you have 3 paths in front of you. You don't know if you are here or here. If you go to the first one, then it means you go here or here, here or here, or here or here. Okay. So it's consistent with what I said. So because of this partial information, the player I cannot distinguish the vertices inside omega ij. And so it means each omega ij is called an information set, because it's a set of information that the player has at this moment. And it also implies, let me just write it like this, it implies that the number of children inside, or for vertices of omega ij must be constant. Otherwise, there would be a contradiction. If you don't know where you are, but once you face 2 paths, once you face 3 paths, it wouldn't be meaningful. And it also explains why we cannot have, I told you, something like this. Because if you think about it, you would have a contradiction. You cannot have the same information. Okay, this case would be a bit special, but yeah. The condition about the fact that this set cannot intersect the play of the game 2 times is also because of this interpretation of, at a certain point, you have the one information, you can repeat exactly the same information later. There would be a contradiction. Okay, and I already explained, but maybe I can still write a sentence. So since we are simultaneously at these 2 points, it's clear that if we take a decision here, it's the same here. So I don't need to, I will just write one more sentence. So we call so W, remember, which is the set of omega ij, ij. This is the information partition of V minus L union omega 0, because it's information, it doesn't, I mean, I already eliminated the leaves, and I also don't look at the nodes due to nature. So it's called the partition information, because we have precisely this information set. And C, which is the set of C ijk, is called, so ij and k is called the choice partition, because you do a choice. Probably, yes, you do a choice when you're at a vertex, you choose one edge, and the only complicated case is precisely when you have 2 nodes or more in one information set, because when you do a choice, it's the same choice here and here, here and here. So the easy remark that I already mentioned, in a sense, if you want to have a simple life, but maybe it's boring, when omega ij contains only one vertex for all I and j, it is simple. And in fact, in graph theory, this is essentially what we did. We didn't consider this kind of set of information or information set where you don't know where you are. So it means we choose just each partition is just one point, and then it's simpler. But the interesting part is precisely that you don't know where, you know, in its life, it's more realistic. You don't always know all the past. You start at one point and you don't know what happened before, so you don't know if you are here or here. So it's quite natural. Any question? Is it clear? Yeah. Again, if you should keep in mind always one example. For everything, if you have one example, not a trivial. Of course, if you take this tree, it's a bit trivial. But if you have an example which is not completely trivial, you can reconstruct the theory, or you can understand what happens. Oh, sorry. I will write again a sentence which contains the same information. Definition for the simple case: if all omega ij contain, if all of them contain only one vertex, we say that the game has perfect information. Has perfect information because you know everything from the past. Has perfect information. If any omega ij contains more than one vertex, contains more than one vertex, the game has imperfect information. So the first case, perfect information, is a boring case. And the second one is probably more interesting. So this definition is quite simple. No, okay. I was wondering if it is somebody from abroad. Yeah, probably we have some people from Hong Kong online. And some people in Japan, of course. Okay, so this definition is rather simple. The next one is a bit more complicated, but it's also interesting. The game is with perfect recall. This is a new term. It's about the memory. The game is with perfect recall if for any omega ij prime inside omega I. So I take two information set for player I. The following hold, or the following condition hold. Okay, so I'm going, on this picture, unfortunately, it's too simple, so I will need to do a slightly more complicated picture. The following condition holds, and we say that it has perfect recall. If X is in omega ij prime, comes after a choice Cijk, then so let me explain. And otherwise, it's called imperfect. I told you it's a bit more complicated, but if you think about it, it's quite natural. So let me draw a picture, a partial picture. And suppose you have a tree and put in red. So we suppose that okay. So this is omega ij for the one player, and somewhere else I have an omega ij prime. It's not the same.
Oh.
There's no contradiction. So this one belongs to a certain set, and this one belongs to another set. It says that if you're in this situation, and we are exactly that, where is X comes? X is this one, this is X. It comes after decision. This is a decision because since it means it is one of these type. It's one of these type. So if it comes after a situation of this type, then all vertices in omega ij prime should be after this one. So it means what is not allowed is this. This is not allowed. We cannot have This part is not allowed. Look, I mean, for perfect recall, this is not allowed because look, this point does not come from this decision. They come, this point and this point come from two different decisions. So it's about the memory. When you are here, there is, I put a sentence, I don't want to copy it, but it's the ability to remember. A perfect recall is the ability to remember. So if the information in, there would be there is a kind of incoherence if you are in this situation with these three, because you wouldn't have the same past histories. But still, we accept it. So we say that it has perfect recall when this doesn't happen. But I guess sometimes it's also interesting to look at this other situation. And so this other situation is called imperfect recall. But the natural one is a perfect recall. So it's a kind of pathology if you don't have perfect recall. So think about it as a set of information. When you are at a certain point, you have information. What is the meaning of perfect recall or imperfect recall? Okay, any question? I will not insist too much on this. On most of the results are when you have perfect recall. Maybe I keep this. Okay. We should have one board just for the picture. So next section, now we describe the setting. Now we want to discuss about strategies. What means a strategy on this? And there are different kind of strategies. And later we will look for equilibrium points like the Nash equilibrium point. So the first definition is about pure strategy. So I will not write it always, but just let gamma be an extensive form. So it means we are in the setting which is represented on the left. So a pure strategy for I, for the player I, is a map or is a function AI from, again, I will explain everything, but we will see that it's quite natural to see. It looks complicated, but on the picture, it will be very simple. It associates to any decision node a decision edge, which assigns, it's a map which assigns to any omega ij a unique Cij. So what does it mean? It means one strategy for player one is, for example, to take this edge I've associate one edge to omega 1,1, and I need to associate one edge to omega 1,2. This is one edge associated to omega 1,2 and one edge to omega 1,3. So it's a choice. And for simplicity, I will put a 1, 1, 1, and 0 everywhere else, simply because I've decided that at this point, I take this decision and not this one and not this one, this edge and not the other two. And then this is for the player one. For the player two, it's a bit more complicated. Player two. Here, this is simple. the player to take one decision. So I put a 1 and a 0. Now, and it's coherent with the notation, I need to choose one edge from this set. So I will choose, for example, this one, but it means I also choose this one. That's why it takes value in the set of Cij, because these two edges are the same. So I can now put a 1 on this one and a 0, 0, 0, 0. So this is a pure strategy. So I did it for player 1 and for player 2. So when it's simple, you just choose one edge. When you are in this complicated setting with an information set which contains more than one point, then you choose an equivalence class of edge. And this is exactly what is written here. Okay. So I define a pure strategy for I, and then since I did it for 1 and 2, so Aj or Ai is the set of pure strategies for I. So how many we have, in fact? Let's take, it's quite easy to count how many we have for the first player. We have 2 choices here. We have 2 choices here. We have 3 choices. So it makes 2 times 2 times 3. So altogether for A1, we have 12. And for A2, we have 2 times 3. So we only have 6 pure strategies. There is an exercise a bit later where I encourage you really to draw a graph and write everything precisely, and you can understand quite a lot. And then I define A, which is this product I from 1 up to n of AI, and this is equal to set of all strategy profiles, so like for the previous games. So it means it is the set of A with A equal to A1, A2 up to AN, and each AI is in AI. So it means I list, it's a vector with one strategy for the first player and one pure strategy for the second player. So we had 12 on 6, so you can guess how many elements are in this set A. It should be 12 times 6, 72. Hope so. I hope I didn't do a mistake. Okay, so we know what is a pure strategy and what is a strategy profile. Is you give a strategy for the first player and for the second player up to the player n. But now we would like to do something a bit more complicated. I don't want to have only 0 and 1. Like nature, I maybe want to have 30% of chance to go here and 0.7 to go here. And the same here, maybe half. Oh no, half, 0.4, and 0.1. It has to sum up to 1. So I also would like to play this game. Not only 1, 0, but sometimes a probability. So this is the next definition, which is no more pure strategies, but it's not mixed strategies. We will speak about mixed strategies in a second, but it's called behavior strategy. So a behavior strategy for the player I is a map. So I will use BI. Again, it has to associate to each decision node for player 1, but now it has to associate a probability. So not only 0 and 1. So if you think carefully, this has to be what I call PS of, it's a bit complicated, but it's quite fun. And then, okay. If you understand this, you can come and replace me. What is it? Look, for each point, you have two choices, and you want to take a probability, and I denote by PS the set of probability on these two objects. Here you have a probability on 3 objects, and so on. So it is precisely take the number of edges starting at ij, we have k, take the probability on this set, and you have this for all nodes for the player I. So it's correct. So, but now let me write the sentence. So it assigns this function, which assigns to any omega ij a probability function on the set Cij k. And I cannot write only on edges it would be simpler on edges starting at this point, but we have this annoying place because here, if I put a probability 1/2 on this edge, I need to put it also on this one. If I put a probability on this one, I need to put the same here and the same here. So that's why it's a bit complicated. When we have imperfect information, we need to deal with these equivalence class of edges. And then you can do the same. Bi is a set of behavior strategies for I. Then you take the product of Bi, you call it B. It's a set of all, before I should have put pure. So in the sentence before, it was the set of all pure strategy profiles. And now it's a set of all behavior strategy profiles. So it means it's a set of B where, so it's a set B, or B has n components, and each of them is a behavior strategy for player I. Okay. So it means now, instead of putting 1, 0, I put a probability distribution or a probability function on each. So what you observe immediately I hope it's clear for everybody. Is this clear for everybody? What do I mean by this? Putting 1, 0 means you put one number on another number. So it's just a very special probability distribution. So this is a distribution where you have 100% and 0%. But it is a distribution. So it means a pure strategy, 0, 1, is inside the set of all possible probability functions. And it also means that A is included into B, because if each player plays with 0, 1, it's the same as playing with a very special probability distribution. So this is quite clear. Pure strategy are simple elements inside the behavior strategy. Okay, but now look at this picture. Nature gave a probability on each yellow edge. The red one put a probability on each red edge, or edge starting at a point in red. And the blue one, player 2, put a probability on all edges starting at a blue point. So it means once you have chosen either a pure strategy or a behavior strategy, plus nature, you have a number on each edge, right? So observation. B or A, but A is a special case. A behavior is, or a pure strategy is a special case of a behavior strategy. And P, which is due to nature, they provide a number between 0 and 1. So it's a number in the interval 0, 1, a number in 0, 1 to all edges of the tree. Because you have given such a number, either made of 0, 1 or made of a probability distribution, but you have a number on all edges. So it means if I fix a x, I can multiply the numbers between the root and this one. So fix a x, you can take the product of this, the number on this edge and the number on this edge. Of take another x, you can take the product of the 3 numbers on edges. So it means you can put a number on each vertex, which is the product of the edges, the number on the edges between the root and this vertex. And this has a meaning. Okay, so we denote, I didn't give a name, but I need to give a name, which is not a good name, but because it's based on B and P, I'm going to denote by, sorry, I was not very inspired. BP of E, the number on edge E. Because it's due to a profile and the function P, which is a nature, it gives a number on each edge. And now I'm going to do what I just said. I'm going to multiply these numbers. Now, for any x which is not the root, we need to avoid the root. We take gamma of x, and remember gamma of x is a path from the root to x, so it means it is x0, x1. Oh, maybe I should, let me put a 1. Okay, no, it has no meaning. x1, x2, up to a xm, which is x. Remember, path is a list of vertices between x0 and x. Okay, so a path is a collection of, so if I go up to here, I need to go through x0, this one, this one, this one, and finally I reach this one. So we take this and define, I'm going to define P of x B. B is a strategy behavior profile. And I'm doing what I said. I'm going to multiply the numbers on edges on this path. So I need to write it precisely, but if you do it on the picture, it's much simpler. It is a product, j from 0 up to n minus 1 of my function BP of the edge E x j x j plus 1. So again, it's complicated. It looks complicated, but it's precise. That's the point. What I'm doing, I define a path from the root to any x, and now I multiply the number on the edges of this path. So you can check, at every vertex, I give a number which is the product of the number on the edges on this path. And it has a meaning. Can you tell me what is this meaning without looking at the notes? It's a probability to go through X, because each, you have 60% to go through this path, then 70% to go through this path, then 10%. So altogether, it gives you the probability to reach this point. So this Px, this Px is the probability that the players will go through X will go through X when they play according to the behavior strategy profile. Wait a second, let me finish the sentence given by B. Davido, please let me finish a sentence.
When we take a path, it goes through multiple strategy profiles because the B corresponds to one.
No, it goes only to one profile. It goes to maybe to the strategy of different players, but one profile contains a strategy of all players. That's why it's strategy profile. B is a strategy profile. It contains information for first player, second player, and so on. And in BP, I have also the information on nature. Now, an exercise for anybody young, any young person, the sum of P Z B is equal to 1 if you sum over the leaves. What is the meaning if I do this for all points, and now I sum the numbers I obtain on leaves? You should obtain 1. At least it's not so difficult, except when you have this strange thing, but I think it doesn't change. No, it doesn't change the computation. It's simply you have put the same 3 probabilities here and here. So it's just a special case. So for this exercise, you just need to compute the probability on these leaves, and you will see that it sums up to 1. Oh, nice. We have 2 good ingredients. Look on the leaves, we have 2 things. So it means, I write it in a sentence, we have a probability function on leaves, because it sums up to 1. Be careful, if you sum everywhere, it's not going to give you 1. It's going to give you more than 1. This is clear if you think for a second, because already after 2 points, you have already 1. Then again, you have 1. So just summing would give you much more than 1. But now we have a probability function on leaves, and we have something else on leaves. We have, I didn't speak so much about this, we have a payoff function. So we have a number associated with, for each player on each leaf. So I can define a new object. And this is now related with what we did for strategy games. I'm going to define, I use blue in the notes, in the new version of the note. I'm going to set, be careful, I'm changing the version on the notes whenever I find a mistake. So now I have a blue UI. for a strategy profile, and I'm going to say that this is a sum on Z belonging to the leaves of P, Z, P, U, I, B for I is equal 1 up to N. This should remind you something. When we discuss strategic games, we define also a new payoff by doing a similar computation with a probability distribution times another payoff. It was red at that time. It was a red payoff based on the original payoff. So we do something similar, and it's meaningful because we are putting some probability to take some pass. So we are averaging these numbers for each player according to the probability that we end up here. So if we have no chance to end up here, we will do 0 times 2, let's say for the first player. We will have 0 chance to arrive here times this payoff 1. If we have 50% of chance to arrive here, we will do 0.5 times 2, then let's say 30%, so 30, and so on. So it's meaningful to take any pass and averaging the payoff according to the probability to be at each leaf. Okay, so probably there isn't. Now it's quite fun. I'm not going to write it, but let me tell you. As we have seen at the beginning here, I defined pure strategies. They are just made of 0, 1. And we counted on this, we had 72. So it's a finite number. So it means I have, in a sense, a finite game with 72 elements in A and a way to provide a payoff at each leaf. So I can define a strategic game, like in the previous section or previous chapter, a strategic game based on pure strategies. But if I have a strategic game, a finite strategic game, I can also construct its mixed extension. It's a bit involved. So it means I'm going to have one more thing. We are going to have, you don't have to write, but we are going to have pure strategies. This I already defined. We have behavior strategies. And we have a third category, which are going to be called mixed strategies or mixed strategy. Can you guess how we are going to construct them? Not you, somebody else. Somebody else. Can you guess, try to guess how we can construct a new object which is not a pure strategy? It's going to be built on pure strategies, but it's different from behavior strategies. I'm going to do a mixture of all pure strategies. So we have, as we mentioned, 72 pure strategy profiles. So I can make a mixture of them. I can take all these 72 and put a probability distribution on them. And then the question, are we going to get the same thing with pure strategies on behavior strategy? It's not clear. But let's keep this for next week. So please, for next week, try to have this picture in mind. I did something in the notes. I wrote all the details. So try to have this in mind for next week, because we are going to do one more thing, and then we will discuss Nash equilibrium. This is not completely important, but it's still a nice piece of construction. Any question or remark? Yes, Havidou.
You can also sum the probabilities, it would be what? If we have distance.
Yeah, but okay. There is a remark which is correct, but if you take all nodes at distance 2, yes, if you take all nodes at distance 2, probably it's correct. But look, the leaves are not at a fixed distance. So what is interesting is the leaves is not the points at a distance 2 or at a distance 3. It's a set of leaves, and they are not always at the same distance. That's it.
But if they are, the same distance,
Yes,
you
but
have a payoff function for each point.
this is a special case.
Okay.
Okay, so thank you and see you next week.